thank you for the introduction. Good afternoon, ladies and gentlemen. I will talk about heat quality assurance measures for high-efficiency solar fields. I want to briefly introduce our company. It's called CSP Services. We're a private company founded in 2007. A bit more than 20 highly specialized and experienced engineers. We're based in Germany and in Spain. We're a spin-off of the German Aerospace Center, DLR. We have our offices close to DLR in Cologne and close to PSA in Spain. What are our main objectives? We implement R&D results in industry to improve CSP technologies. What's the benefit of that for the CSP industry? We lower technical risks, improve project performance, and improve competitiveness. For investors and owners, this is lowering investment risks, increase solar power production, and thus rise profitability. And also for society and environment. We want to reduce solar electricity costs, reduce CO2 emissions, and provide a sustainable energy supply. Well, the motivation for quality assurance, we all know the solar field has a high share of the total investment costs of a CSP plant. It's a long-term investment and it has a large extension, so adjustments or repairs are expensive or not even possible. And the plant output strongly depends on the collector field quality. So the range of 3 to 10% can be easily lost in performance if you don't do correct quality assurance. The quality assurance is necessary for ensuring the expected plant performance, control of your subcontractors, and for warranty claims. And just a simple example on the importance of high quality components on the project economics. Based on a standard 100 megawatt electric parabolic trough power plant, say we have two types of mirror panels. Just an example of components. You can do that for all components of two different qualities. One is a mirror with a reflectivity of 49.5% and a low degradation rate, and an FDX, that is the shape accuracy of 7 millimeters, and it costs €25 per square meter. And you have a quality B that has slightly lower performance numbers and is, well, significantly cheaper in price. So you don't really know what is the better choice. You definitely need to make a techno-economical analysis, as speakers before already told, to look what does it mean. If you look at the technical performance over the 20 years of your lifetime of the power plant, you can see that the difference in average performance is about 3% for this example, 1.5% from the reflectivity, and 1.5% from a lower intercept factor. Now, if you look at the economics, say, well, a mirror surface of 1 million square meter, so type A costs about, well, $5 million less than type B. That's quite a lot of money. But then if you look at the revenues over the lifetime of your plant, 20 years, 3% difference translates to almost 30 million. Well, this is now a very simple example. It doesn't take into account interest rates and other plant operation things. You have to do that much more exactly, but it gives you an idea that a small loss in performance can have a huge effect in your revenues. So it's better to spend a little bit more at the beginning and have a good quality component and a good quality plant, and that will save you a lot of money on the long run. So these are the 2 points that we can point out. High quality components and durability is often more important than just the price. You need to look at both. And quality assurance has a relatively low cost on what you can lose if you don't do it. So it's well worth the effort. Now, if we look at the typical efficiency chain for a parabolic trough, this graph can be done similarly for other technologies such as solar tower or Fresnel. We start on the left side 100% with the solar irradiation, and then we have different effects and losses, and we end up on the right side for normal incidence with an optical efficiency slightly above 75%. This is an example just to show the different effects and what needs to be considered. So if we start on the left, solar irradiation, or DNI, this is measured by the resource assessment, usually before you build the plant. And it is very important to know if you really have that 100% of DNI available. For that, you need high quality ground data from the site and also long-time satellite data. You can put this two together, and then you get a high quality, long-time evaluation of your solar resource. To have high quality in the ground data, maintenance is very important. It's not sufficient to have a highly accurate measurement system if you don't clean it or if it's not correctly installed. And we recommend that often the rotating shadow band irradiometers that you can see here on the right side often performs better for remote sites where maintenance cannot be done daily, because it has a lower sensitivity to soiling and thus delivers better results. So our recommendations on that would be to use economic RSI stations, ask for frequent maintenance, and for high quality data service. The next block of effects can be attributed to the collector design. These effects or efficiency is here influenced by cosine effects, incident angle modifier, shading and blocking, end losses and intercept factor. And our recommendations are to use mature designs, adapt them to local production possibilities, cross-check the drawings, and build full-scale prototypes before you go into a commercial plant with a new design. And also perform extensive geometric, structural, and thermal tests on the prototype before you go in large scale. The next block of effects can be attributed to the mirror panels. Their efficiency is determined by the solar-weighted specular reflectance. It's important that it's specular reflectance, not hemispherical, and it must be solar-weighted, not just for a certain wavelength, because that's what you actually, that's the energy that you get. And the shape accuracy. That's for parabolic trough panels, usually the focus deviation, or FDX, as the quality parameter. And for sure, degradation. One thing is the quality that you have at the beginning, but you also have to keep in mind what is the quality that you have during the whole lifetime. State of the art for an RP3 mirror panel is that reflectance, solar-weighted specular reflectance, should be above 94% and focus deviation below 7 millimeters as an RMS. Recommendations on that is that you should specify high quality, state-of-the-art in the tender documents, claim long-term warranty in the procurement, evaluate offers in respect to costs and quality, that is important, and confirm the stated quality for new manufacturers or unknown qualities. Confirm it in independent expert laboratories. And also claim for regular sample measurements in fabrication with traceable documentation and using proven inspection systems. As an example, you can here see the QDEC system for mirror shape accuracy measurement and a typical measurement report. Next block of effects can be all attributed to the receivers. Well, we have heard about that in one of the previous speakers. Their efficiency is determined by the transmittance of the glass cover tube, the absorptance of the steel tube, heat losses, the bellow design, that is the effective length of the tube, the active length, and degradation. And state-of-the-art for the 70 millimeter tube is the optical efficiency in the range of 106% relative to DLR reference, and transmittance higher than 96%, and heat loss in the range of 230 watts per square meter at 400 degrees. Again, our recommendations is to specify high quality in the tender documents, claim long-term warranty, and evaluate the offers in respect to costs and quality, and confirm the quality in independent laboratories, and also claim for the sample measurements in fabrication. Here you can see an example of the DLR lab and a measurement report for the heat loss of a receiver tube. Now, for assembly and installation of the solar field, it looks in this graph as if it had only little importance, just on the intercept factor and just one part of the intercept factor, so it looks like it's really not to worry about, but actually this is the part where most can go wrong during the construction of the solar field. The efficiency in this case is the intercept factor. It is well, the intercept factor, you probably all know, is the factor between all the reflected rays and the ones that actually hit the absorber. It's influenced by the accuracy of the concentrator structures or the mounting of the reflector panels, deformations caused by gravity, wind, friction, by receiver and module alignment, and the tracking accuracy. And I have listed here some numbers and what is state of the art for high quality concentrator. That's the mirror support bracket position. That's the position of the mounting points. They should lead to a mirror tilt of below 0.8 milliradians. The mirror support bracket angle, that is the angle of each point where you fix the mirrors to. This angle, if it's wrong, can lead to deviations of the mirror shape, and this effect should be below 1 milliradian. The receiver alignment should be below 3 millimeters. The module alignment relative to the drive, also below 1 milliradian. Collector torsion, that is the torsion between the drive and the last module. That should be, as an RMS, also below 1 milliradian, and the tracking accuracy also below 1 milliradian. So you can see all these effects should be in the range of a milliradian or below to have low impact on performance. If you have one or two higher, significantly higher than that, then this will be the one that actually causes the main part of the losses. A small side note on intercept factor check. We can perform measurements with the so-called camera target method, where a white target plate is positioned perpendicular to the absorber tube, and then pictures are taken from the incoming rays. You can see on the right on the lower part, and the missing rays, if there are any that miss the tube. We can do this for many positions along the collector, and then based on these images that we have, do an analysis on the intercept factor, and we get graphs like this that shows the intercept factor for each picture or each measurement position along the entire collector of 12 modules. And you can see the first measurement was done is the red one, where you can see that there are some issues. Intercept is in average only 88%. There's some systematic effects. At the ends, it's lower than in the close to the drive, but also from point to point, quite some jumps. So this was analyzed in more detail, and then correction measures were proposed and realized. The collector torsion was corrected, the receiver tube alignment was corrected, and also the tracking. And then the same collector had, you can see now the green curve, achieved an intercept factor of 97%, and is perfectly good. So it's difficult to get higher up than the 97%, but if you don't check it, you can easily commit an error and be below what you actually expect. So for the assembly and installation of the solar field, our recommendations, again, specify high quality, state-of-the-art antenna documents, claim warranties, and evaluate the offer's respect to costs and quality. If it's a new design, check or new companies that build that and procedures, elaborate suitable process descriptions for the assembly and check prototypes. Check the components that you use during the field fabrication, and also to frequently check the geometry of the structures that you build, so that you have a continuous quality assurance of the quality of your structures that go out to the field. And one point, the last one, is also important in our point of view, that the first modules and collector that go out in the field should be thoroughly checked once they're in the field. If there are any issues that you are still on time to correct in the production before you build the entire field. If you notice in the end when you do the thermal test, but you already have built the entire solar field, you notice that there was some mistake in transport, in mounting, and whatever. It's very difficult and very costly to correct that. Details on this are given in this paper. You have the reference in the presentation. Finally, the cleanliness of the mirrors and the absorber tubes. That is an O&M cleaning optimization that needs to be done site specifically and depending on the cost to have an optimum between clean mirrors and tubes and O&M costs. There are several European testing centers, which show a selection here where component tests and independent tests can be done. This is the DLR with the Quartz Center in Cologne. Also the OPAC laboratory that is in Spain, operated together CIEMAT, Spanish CIEMAT and DLR. And also we at CSP Services can provide such services, which I show a little bit in more detail in the following slides. At the DLR Quartz Center, mirror panel performance tests can be done, so you can send mirror panels there and they can be tested for shape accuracy and for reflectance. You can also send receiver samples there and they can be tested for optical efficiency, thermal power loss, overheating and thermal cycling, and bellow fatigue tests. And there's an additional test bench that DLR operates in southern Spain on the PSA. It's called CONTAS. It's a parabolic trough module on a turntable where absorber tubes can be tested under real solar conditions. In the OPAC laboratory at PSA, all types of accelerated aging tests on mirrors can be done. This is to show if there are any degradation effects and that, to make sure that you have over your whole plant lifetime a high reflectivity of your mirrors. And finally, CSP Services, we provide measurement systems for quality assurance in the CSP sector. That is automatic weather stations for the solar resource assessment, the QDEC mirror shape inspection system for the measurement of shape quality of mirrors in the production, the QPhoto inspection system for the measurement of concentrator structures in the assembly of the solar field, and the QREC, that's two types of receiver, optical and thermal test stations for the manufacturers of the absorber tubes. We also offer on-site expert services such as solar field inspection and expert consulting, concentrator shape measurement of installed prototypes or solar fields, alignment measurements of mirror, receiver and module, local intercept fact measurements, thermal efficiency measurement, and also weather data check and TMYs, and we do the handling of the measurement services for the DLR Quartz Center. So, we have a lot of experience in this type of measurements, certifications, and consulting, as we have worked in the past years with many important companies in the CSP sector, and we're happy to help you in your applications and your requirements with our products and services. To summary my speech, well, quality assurance is essential and makes economic sense. It prevents technical and financial risks. It improves project performance and long-term profitability. And the required testing methods and infrastructures, test labs are available. And quality assurance for CSP includes the solar resource assessment, collector and solar field design, component qualification, assembly and installation, and operation and maintenance. And to summarize it even a little bit more in just one sentence, the high quality components and correctly implemented quality assurance saves a lot of money. Thank you for your attention.